Welcome to massive open online course on basic principles and calculations in chemical engineering. So, we are discussing about process variables and rate under module 2. So, under this module 2, today we will discuss more about that process variables like pressure and temperature of flow processes. We have discussed in the previous lectures some process variables and their principles, what is system, even physical and transport properties of material in system and mixers. So, in this lecture extension of that part we will something more about that process variables like pressure and temperature, fluid statics and their measurement in flow processes. We will try to learn something about this. Now, the pressure at the base of a vertical column of fluid that is not moving and whose density will have a certain value, and if it is denoted by rho and the fluid height is h, then this pressure exerted by this particular height of this liquid in the container of that particular density, it will be regarded as that hydrostatic pressure, and it can be defined as this rho z h. So, here see in this figure in the slide, you will see that in a container some amount of fluid whose density is rho is kept there, and here you will see that this amount of fluid will exert pressure at the bottom of this container, even at its wall of this container at a certain value. Now, this pressure you will see that will be equal to rho z h, it is called hydrostatic pressure. That means, what will be the length of this or height of this fluid that shows by this fluid or liquid in the container, and also what will be the density of that fluid. If you know that, then you can easily calculate what should be the hydrostatic pressure. But this total pressure will be what? You will see at the surface of this container some atmospheric pressure will be acting on this container, and this atmospheric pressure, if you add on this hydrostatic pressure, it will be total pressure that is acting on this bottom of this surface, bottom of this container there. So, it will be regarded as total pressure here. So, this total pressure is here this atmospheric pressure and the hydrostatic pressure. So, this atmospheric pressure is represented by P0 here as shown here, and hydrostatic pressure will be equal to rho z h. So, the summation of this atmospheric pressure and hydrostatic pressure will be total pressure that is exerted by the fluid and atmosphere on this bottom of this container. So, we can say that if a vertical container contains a fluid, the mass of the fluid will exert a force on the base of the container. So, this is the basic of this hydrostatic pressure whenever fluid will be kept in a certain container, and then what will be the pressure exerted by that total mass of this fluid that you can get by this hydrostatic pressure. Now, interesting is that sometimes this pressure will be represented by head, because it is it will be sometimes regarded as what is that length of the fluid there, and by which the hydrostatic pressure will be sometimes will be represented. Now, in this case the height of a hypothetical column of this fluid, if it exert certain pressure at its base, and if the pressure at the top will be 0, then from that hydrostatic pressure equation we can say that it will be simply P is equal to rho z h. So, here this rho z h, from this equation we can say that here H will be is equal to P by rho Z. So, this H will be called as head. So, pressure is sometimes regarded by this head and its unit will be is equal to unit of the length, because this is simply height, but this height you can get it from this equation, because P is what is that unit for P is Newton per meter square, whereas you will get that this rho g h unit will be equal to what. So, accordingly after vanishing that equation and also that units, so finally you will get that unit of this head will be h or length, or you can say that meter there. So, the advantage of expressing this pressure as a head is that this quantity is now independent of the material properties. So, that is why sometimes the pressure is represented by head. And now important thing is that what we told that there will be some hydrostatic pressure on the fluid element. Now what should be the pressure if you have this certain distance or certain height of that liquid, you can easily calculate this this hydrostatic pressure. But sometimes you will see that you need to express this hydrostatic pressure in more general format, and how to derive this hydrostatic pressure, that you can have from a consideration of certain fluid element that is kept in a container, or if it is flowing through the conduit, then from that fluid element we can easily derive some expression of this pressure within a static fluid element. So, in this case if we consider that a fluid element of volume of dimensions like here x, y and z, and its volume will be as dx into dy into dz. So, in this case here if we consider this this fluid element here as shown in the figure in this slide, you will see that the pressure P will be acting at the center of this fluid element, and it will have 6 faces, and on all these 6 faces the pressure will be acting from all its directions. So, you will see that if we consider that x, y and z directions, now if we consider this the element of this volume of dimensions like dx, dy and dz in x, y and z direction, then we will get, or we can consider that there will be a 6 faces. Now, on each face what should be the pressure that is exerted from surrounding fluids. So, in that case we can express this total force that acting on the element will be actually as dF. Then this dF means here small amount of force will be acting over the small volume of fluid element that we consider here. So, total force acting on the element will be dF. Now, this dF actually will be sum of the body force and what will be the net surface force acting over this small fluid element. So, this small fluid element will have some body force, that is that will be regarded as gravity force. So, this body force and what will be the total force acting over the surface of this fluid element, that will be as net surface force, because here two forces will be subjected to the pressure from the opposite direction here in this fluid element. Like in the x direction, if you consider that in this direction the force will be acting, and from this direction also force will be acting. Now since this force will be acting in the opposite direction, then there will be some net force will be acting on this in this x direction. So what should be that net surface force that you have to calculate? So what should be the first you have to calculate body force. So body force will be equal to what? We know that gravity force, that will be equal to m into z. So what is m here? Since we are considering the fluid element of volume dx, dy and dz, this is volume. So if you know the density of the fluid, what should be the mass? So volume into density, that will be your mass. So you know that density is rho and volume is dx, dy and dz. So we can write rho into dx, dy and dz here. So this will be your mass, and if you multiply this mass with this gravitational accelerations, and then you can say it will be your body force. Then you have to calculate what should be the net surface force acting on 6 faces. Now first you consider in x direction. So what will be the force acting on this face here as shown in the figure. So that will be your, what is that, p plus dou p dou x into dx by 2 into dy dz. Why it is coming like this? You know that force is acting at the center as p, whereas you will see that since this face here this what face we can say here, this is simply that here dy and dz, dy dz. So this face will be at a distance of at a distance of dx. So what will be the pressure gradient there at this face here? So it will be dou p by dou x. Now since this pressure gradient will be at a length of dx by 2. Why dx by 2? Because from this face to this face total distance is x. So here since from the center to this face is dx by 2 distance, then we can have this distance as dx by 2. Now if you multiply this pressure gradient over this dx by 2 distance, then we can have that pressure difference over this dx by 2. So this pressure difference will give you this what will be the pressure at this surface there. So this at this surface in the positive x direction, we can easily say that at this point what is the pressure, and at this surface what will be the pressure there. So it will be p plus dou p dou y into that dou y by 2 into dx dz. So in this way we can calculate what should be the that net force here. Only that you have to calculate first in this positive direction what will be the pressure, and in the negative direction in the same way what should be the pressure there. So if you subtract this positive to that here this side of pressure, then you can easily express by this equation here. So this will be your in the x direction. Similarly in that dx dz plane or face, you can express the pressure like this here. Similarly in this dx dy plane or face, you can express what will be the net force over there. So if you add all those net force acting on the 6 faces, then you can get here this equation minus dou p dou x plus dou p dou y plus dou p dou z into dx dy dz. So, in this way you can calculate what should be the net force acting on 6 faces. Now, substitution of this net force and the body force in this equation here of total force acting on the element, that can be expressed then by this equation here. So, dF will be equal to minus dou p dou x plus dou p by dou y and plus dou p dou z into dx dy dz plus what is that body force is there. As per Newtonian law, we can say that this small amount of force, that will be equal to mass into acceleration. So, if we consider that small amount of mass is that dm and its acceleration is a, this acceleration will be that in x direction, in y direction and in z direction also. So, we can write here what will be the dm here, rho dv into a. Rho is the density and dv is the small volume, that is dux dy dz, and then rho into dv it will be mass, then into a it will be acceleration. So, it will be called as force as per Newtonian law, or you can say that as per that Newton's law of force there. So, it will be that mass into acceleration, and for static fluid we can say that there will be no acceleration. So, a will be equal to 0. So, in this case we can have this df will be equal to 0. Therefore, if we substitute this df here this left hand side and that will be equals to 0 by this equation, then we can say that minus of here dou p dou x plus dou p dou y plus dou p dou z plus rho g, that will be equals to 0. In this case g is gravitational acceleration. This acceleration will be acting that it is in general that g can be regarded as general here, but if it is working in vertical direction, then you have to consider it as gravitational acceleration. Otherwise, in either direction you have to consider as a certain value of acceleration there other than gravitational acceleration. Now, this g if we consider here which is equal to 0 in x and y direction, that means in the x and y direction there will be no acceleration, since the fluid element is in static condition. So, in the z direction we can say that g will be equal to gravitational acceleration, and this gravitational acceleration will be equal to 9.81 meter per second square. So, finally, after substitution of this g in that z direction, we can easily say that minus dp dz, that will be equal to minus rho z. So, from this we can say that here p1 minus p2, that will be equal to minus rho z into z1 minus z2. This is z1 minus z2 is the distance between 2 points, and p1 minus p2 will be equal to pressure between 2 points. So, in this case, as per figure shown here in the slides, if we consider the 2 points here on this fluid element at the surface, you will see that if we represent here or denote here as point 1, and at a depth h, the point here 2, then you can say that at the point 1 you will get the pressure only atmospheric pressure, whereas at point 2 you will get the pressure here at a certain height of h. That h will be equal to hydrostatic head, and based on this you can express by this equation as P0 minus P2, because here at this point 1 pressure is P0 atmospheric pressure, and at this point 2 pressure is here P2. So, we can write here P0 minus P2, that will be equal to minus rho z into what is that, what is z minus z, z1 minus z2 here at this 1.1. since we are considering that datum line is at point 1. So, here distance is 0 and what is that here A is Z2, Z2 is basically, since it is in that negative Z direction, it will be minus S. So, 0 minus of minus S, because Z2 here it will be equal to minus S. So, ultimately we can say that this P 2 minus P 0 will be equal to rho z S. So, this P 2 will be equal to then P 0 plus rho z S. Now, this P 0 is the atmospheric pressure. So, in this way we can derive this hydrostatic pressure based on the consideration of the small fluid element at its static condition in x, y and z directions, and considering their force acting on that fluid element from all the directions at a certain amount. So, based on which we can derive like this what should be the hydrostatic pressure there. And so, we have got this we have got this very interesting equation here. This this will be equal to P1 minus P2, that will be equal to minus rho z to Z1 minus Z2. This you have to remember, because this equation will be useful to estimate the pressure of the fluid flow whenever it will be flowing through the pipe or any other conduit or any other system or any other unit where you need to calculate, you have to estimate, you have to obtain the pressure between 2 points, and this equation will be helpful to calculate. So, we will give some example also there how to calculate, how to use this equation to calculate the pressure there. Now, the earth atmosphere can be considered as a column of fluid with 0 pressure at the top, and the fluid pressure at the base of this column, like at sea level, is the atmospheric pressure that you have to consider, and the absolute pressure of a fluid is the pressure that is relative to a perfect vacuum there, that will be P is equal to 0. And gas pressure is basically that is pressure of the fluid, which is the pressure of the fluid relative to the atmospheric pressure, that is reference pressure. A gas pressure of 0 indicates that the absolute pressure of the fluid is equal to the atmospheric pressure. So, you have to that use this equation or remember this equation to calculate the absolute pressure. Basically, whenever fluid will be flowing in a system, and the pressure whatever it will be exerted without consideration of atmospheric pressure, it will be regarded as gas pressure. So, absolute pressure will be basically the gas pressure plus atmospheric pressure. So, in this way you have to remember, whereas gas pressure will be what is your absolute pressure. If you subtract that, what is that atmospheric pressure, you will get the gas pressure there. So, you have to remember this equation, what will be the atmospheric pressure. Atmospheric pressure will be equal to gas pressure plus absolute pressure will be equal to gas pressure plus atmospheric pressure. What is the unit for pressure that we told? Newton per meter square. In CGS unit it is 9 per centimeter square, whereas in American engineering system this unit will be PSI, that means pound force per inch square. And what are the different types of pressures? You know that atmospheric pressure, absolute pressure, gas pressure and vacuum pressure. Vacuum pressure is a gas pressure that is below atmospheric pressure. Even other than these pressures, you will have different types of pressure whenever fluid will be moving through a pipe or any other system. Like you will see that whenever fluid will be flowing, the measurable pressure, total pressure will be actually summation of this hydrostatic pressure and frictional pressure, and also if is there any pressure because of that change of cross sectional area, or any heat energy supplied to the pipe, or any other that force acting on this conduit or not, like magnetic force, electrical force, or some other force, or if any change of momentum is there inside the pipe or any system there. So, in that case the total pressure will be equal to pressure due to friction, pressure due to hydrostatic pressure, and pressure due to the change of momentum, or pressure due to the other because of other exerting force on the system. So, these are the various types of pressure that you have to remember, and you have to know also what is that standard atmospheric pressure. It is defined as the pressure that is equivalent to 760 millimeter mercury or 1 atmosphere at sea level and at 0 degree centigrade. So, this you have to remember. So, in this case 1 atmosphere will be equal to what is the 760 millimeter mercury. That means, in a column if you take mercury, and you will see what will be the pressure if you take that mercury of length of 760 millimeter length. So, in that case what will be the total amount of hydrostatic pressure because of that mercury, it will be actually equivalent to the atmospheric pressure. So, it is actually after calculation of, because here that will be again that rho z into H, rho of mercury of density of mercury, it will be 13,600 kg per meter cube, G is 9.81, and that H is here, it is 766 millimeter. You have to convert it to meter, that means that what is that 7.60. In that case you will see that centimeter, sometimes it will be represented as 76 centimeter mercury, and you have to convert it to meter like 0.760 meter. Then if you multiply that density like 13,600 into that 9.81 into 0.760, then you will get that atmospheric pressure as like this 1.013 into 10 to the power 5, that will be equal to Newton per meter square. So, it is regarded as what is that Pascals also. So, it will be 101.3 kilopascal, just divided by 1000, then you will get. Even this will be regarded as also bar, like 1 into 10 to 1.013 into 10 to the power 5 pascal, it will be called as 1.013 bar. Similarly, this standard pressure can be represented by that AES system, that will be it will be equivalent to 14.696 psi, or you can say that 14.7 psi. So, it is also will be equivalent to 29.92 inch of mercury, and also you can say that it is 33.91 foot of water column pressure there. So, in this way we can represent that standard atmospheric pressure at different or by different units. Now, there are some conversions of pressure from one system to another system. It is given in this table in the slide. You can go through this conversion. This conversion table may be useful for your further calculation. Now, standard and normal temperature and pressure, what is that? You have to know that standard temperature and pressure are used widely as a standard reference point for expression of the properties and processes of ideal gases. So, in that case STP is set by IUPAC as 0 degree centigrade, and 100.325 kilopascal or 1 bar. This STP means standard temperature and pressure, whereas NTP is another condition, it is called normal temperature and pressure. It is set at generally 101.325 kilopascal, but the temperature will not be 0 degree centigrade, whereas it will be 20 degree centigrade there. So, there is a difference of this STP and NTP is that pressure will be same, but temperature will be different. In case of STP, the temperature will be 0 degree centigrade, whereas in case of NTP the temperature will be 20 degree centigrade. And also you can say that this pressure, whatever we are getting, that standard pressure or pressure in a particular system, how to measure that pressure. There are various types of pressure sensing devices are available to estimate the pressure or measure the pressure whenever fluid will be flowing through the pipe or through the other systems there. Like here the Burden gauge, diaphragm, capsule, capacitance sensor, column of fluid, manometer, barometer, silicon diaphragm and semiconductor strain gauges are used to measure this pressure. And in laboratory scale, even most of the cases the manometer as a U-shape device that are considered to measure or are used to measure that fluid pressure there in the system. So, this manometer is a U-shaped devices that uses a fluid having greater density than other fluids in the process unit. So, this is very useful, and these manometers are actually inexpensive and simple, and also it will give you that accurate measurement. These are basically used to measure that fluid pressure in the system. And also we can say that there will be a certain principle of that manometer by which you can calculate the pressure. So, there how it works, that manometer to there in the fluid system to get the pressure from this manometer, that you have to know. So, a manometer is a U-shaped device that I told that is being used for measuring that fluid pressure, and in this case whatever fluid is being used, generally it will be higher density relative to the fluid that is flowing through the system. And it works based on the fact that hydrostatic pressure at the same level in the same fluid must be same in each leg of this U-tube manometer. So, the schematic of the U-tube manometer is shown here in the slides. It will have that two legs, the left leg and right leg. You will see in the U-tube manometer some fluid that will be higher in dense relative to that other fluid that is flowing through the system. And in this case this higher density fluid, whenever pressure will be subjected on this manometer leg, you will see that the fluid will be moving up little bit, and there will be a difference of this fluid level, or you can say that liquid level inside that manometer, and based on which you can calculate what should be the hydrostatic pressure exerted by that fluid in the system. So, whenever we need to determine the hydrostatic pressure that is caused by a mass of fluid, it is simply given by that gauge pressure, that will be as P, that is F by A, that is mg by A, that is mg means rho Vg by A, rho is the density, V is the volume, and G is the gravitational acceleration, A is the cross sectional area, and then you can say that rho into A into H here as shown in figure here. Suppose this right leg of this fluid will be above this S level of initial or left leg level. So, what should be that force exerted by that liquid that is shown in within this length of H there. So, here in this case you can say that it will be rho into A into H into G by A. So, it will be simply rho into G into H. So, here absolute pressure will be equal to this gas pressure plus atmospheric pressure. So, whatever hydrostatic pressure will be based on this small h of this fluid element, it will be recorded as gas pressure, whereas on this gas pressure there will be extra pressure, that is atmospheric pressure will be acting on that on the surface, then it will be that atmospheric pressure. Now, sum up of this gas pressure and atmosphere pressure will be equal to absolute pressure. There are various types of manometer are generally used to estimate the pressure. Basically, three different arrangements of the manometers are actually used to measure this pressure using a column of a dense liquid. One is open end manometer as shown here. In this case, the one end of the leg, that is you can say this is manometer. So, one end of this manometer will be open, that is why it is called open end manometer, and another is differential manometer. In this case, both the leg will be connected to the process system, or like if there is a fluid is flowing through the pipe, then at the 2.1 and 2 this manometer leg will be connected. So, it will give you that pressure difference, that is why it is called that differential manometer. In this case, you have to remember that the pressure decreases in the direction of the flow. So, that is why if pressure is given like this at P1 and P2 at this point 1 and 2, you will see that at point 2 pressure will be lower, whereas at point 1 pressure will be higher. So, that is why the pressure will decrease in the direction of the flow. So, the pressure difference will be equal to P1 minus P2, or if you are considering that P2 minus P1, it will be as negative delta P or negative pressure difference. A closed end manometer also used to actually calculate that absolute pressure. In this case, a manometer that has one leg sealed and the other leg open measures the atmospheric pressure. So, in this case, very interesting that one leg sealed here like this, and another leg that will be connected to the process system, and it is called that some like it is called the barometer or something, and they are in this case whenever there will be any seal of that right leg there. So, in between that denser liquid and that seal end, there will be open space, not open space, it will be a space there, but that will be that certain amount of gas may be present or may not be present. So, if there is no gas is present, there will be pressure will be 0, whereas if some gas will be there, there may be that some pressure will be exerted by that press there, that you have to consider. So, in this way this closed end manometer is also used to calculate the pressure difference. Sometimes inclined manometers are also used. It is generally conventional installment of pressure measuring instrument as per that that condition of that process unit where it will be installed there. So, sometimes the inclined manometers also is used to calculate the that pressure difference there. So, in this case also here the same principles is being followed like hydrostatic pressure, but here the that manometric height that will be actually will be shown in here. In this case it will be inclined, but for the calculation you have to calculate what should be the vertical height of that, just because of what is that inclined angle it will come, and based on which that inclined angle what will be the vertical height for that, you have to calculate based on that angle, and based on this that vertical height from its inclined leg you have to calculate what should be the that is hydrostatic pressure, and that pressure will be actually gauge pressure of your that system. General manometer equation, if we consider that, what you have to remember, for the balancing of that pressure on its both sides, you will see that in one leg will be connected to the process system, another leg may not be there. So, in one leg whenever a system will give you some pressure on that particular leg, so there are some force will be acting on that, and because of which this what will be the manometer fluid will be used, that manometer fluid will be rise on the right leg of the manometer, and on that right leg if it is kept open its end, then atmospheric pressure also will be acting on that open end surface of the manometric fluid. So, in that case on the both leg there will be a force acting, but at a certain condition this manometric fluid will remain static there because of that force balance. Now, from that static condition of that manometric fluid rise, from there you can calculate what should be the pressure just by balancing that force acting over that manometric fluid on both sides of the manometer leg. So, that is why you have to calculate what should be the pressure, summation of pressure on that leg 1, that is in the left leg, and what would be the summation of pressure on leg 2. So, here I have shown in figure in the slide that here the leg 1, here this is leg 1. In the leg 1 you will see that this is the fluid whose density is rho 1, that will be coming from the system, maybe since it is connected to the process unit, the system, and then this liquid will be as what is that manometric fluid, maybe higher density, that density is rho 3, that may be mercury, and other part here it will be some other fluid may be there, it may be the same of that left leg or maybe other fluid also, whatever it is, but its density will be certain there. If it is not same from that left leg, then maybe other dense fluid like as density rho 2. So, at this leg we are having what is that some P2 here pressure due to that this fluid of rho 2 and the pressure due to this of fluid of density rho 3, and at this leg in the left leg, leg 1, you will see that pressure will be exerted from that system, and then pressure will be exerted by this fluid of density rho 1, and here also you will see that what will be the pressure at this point. Now, very interesting point here that you have to consider some datum line, at a particular datum line from which you have to calculate that summation of the pressure on the left leg and summation of the pressure on the right leg of this manometer. So, that datum line or reference line is to be considered, otherwise it will be very difficult to calculate. you can decide the data line anywhere in this manometer leg. Maybe you can consider at the bottom of this manometer leg here itself. See, I can show you like this, but you can conveniently decide this datum line here at this fluid interface of this manometric fluid and the other fluid inside the manometer. So, it will be better to consider the datum line here at this point where manometric fluid and other fluid give the interface. Otherwise, you can also try it, you will get the same results if you are considering the datum line at this bottom. So, from this bottom you have to know what will be the distance there, that distance you have to calculate from this bottom line. Now, if I consider that bottom line as shown here in the slide as dotted line like 1, 2, and what should be the then total pressure at this bottom leg of this manometer? It will be here at this point here, this is P1, that is P1, and the hydrostatic pressure that is exerted by the fluid of density rho 1 and its height is regarded as H1. So, its hydrostatic pressure will be rho 1 into Z into H1. So, it will be your hydrostatic pressure that is exerted by fluid of density rho 1. Now, this is your up to this datum line, what will be the total pressure. Now, if you consider the right leg of this manometer above this datum line, you will see that above this datum line this manometric fluid is raised up to what is that H here. So, from this to this point the height is H, and from this to this point the height is H2, and above this H2, above this point this pressure is P2. So, in this case total pressure will be this summation of this P2 and pressure exerted by this fluid of rho 2 of height H2 and the pressure exerted by this manometric fluid of density rho 3 of height H. So, total pressure will be equal to P2 plus rho 2 into Z into H2 plus here rho 3 into Z into H. Now, both the total pressure will be same at its static condition of this manometric fluid inside this manometer. So, from which you will be able to calculate what should be the pressure difference between P1 and P2. So, from this equation you can say that P1 minus P2 will be equal to here rho 2 Z into H2 plus rho 3 Z into H minus rho 1 G into H1. So, in this way you can calculate what should be the pressure between 2 points if this manometer is connected to a certain system. Like here one example is given to you, like a nitrogen gas is kept intact in a tank as shown in figure here. The pressure exerted by the gas is measured by a closed ended manometer. The manometer fluid is of specific gravity of 0.87. The manometer shows the elevation difference of 0.01 meter. So, in this case what should be the pressure inside the tank? Now, what you have to do? You have to calculate the gas pressure inside the tank. Now, this gas pressure will be equal to what? So, it will be equal to that rho Z into H, that is given by this manometric fluid rise from this interface, that is at H, whereas inside this that manometric fluid there will be vacuum, that will be Pa will be equal to atmospheric pressure will be equal to 0. So, that will be your tank pressure here. So, what will be the tank pressure here? That will be equal to 0.87 into 1000 into 9.81. Okay, because here H is given to you, that and also what is that specific gravity is given to you, and also this gravitational acceleration is there. So, what is that manometer specific gravity is 0.87. If you multiply this specific gravity with the density of water, you will get the density of fluid of this manometric fluid, and and then G is that, and height is given 0.01 meter. So, finally, it will be coming as 85.3 Pascal. And then another example, if suppose a gas is flowing through a pipe as shown in the figure here in the slide, an open ended manometer is connected to measure the pressure of the flowing gas inside the pipe. The manometer fluid density is 2.0 gram per centimeter cube, and it is seen that a gas bubble is trapped in the left leg of the manometer here. Gas bubble is trapped here. Now, in this case you have to calculate the pressure of the flowing gas inside the pipe. How to calculate? See, here very interesting that the manometric fluid will be there inside the manometer, but during that flow some gas bubbles is trapped inside the manometer. Now, this because of this trapping of this gas bubble, there will be a pressure, whatever pressure will be exerted here, that will be balanced by this that here manometric fluid up to this rise. Now, if it is there, then how to calculate that pressure here? In this case, if we consider that the datum line as x dash x here at this interface. So, we can say that at the left leg, what should be the pressure, that will be at x, in the right hand leg, that will be x as Px. Px will be is equal to what here, rho Gh plus atmosphere, because this rise is given because of this, what is that, total pressure in this that left leg, and this pressure is coming because of this gas inside the pipe. Now, then what will be the Px here at this, that will be is equal to rho into G into H plus this atmospheric pressure. So, rho is density that is given to you, and G is given to 9.81, and H is 0.12 meter, it is given to you, and then atmospheric pressure you have to add. So, finally, you are getting 0.0232 atmosphere plus P atmosphere, that is atmospheric pressure. After that, you have to calculate what should be the pressure at that left leg of this manometer, that is at point that x dash, that is P x dash, it will be equal to here P gas plus here P gas here, and also what is that, in this case gas, rho gas into G gas plus into H gas. This is also hydrostatic pressure because of this gas present here, and also fluid like this here, this that fluid, this is this 0.10 meter here fluid. So, in that case rho fluid into G fluid into what is that, H fluid you have to calculate. So, finally, you can get that this P gas plus here at this condition there will be no gas bubble, there will be no pressure, here also there will be no pressure. So, finally, you can say that this portion will be equal to 0, whereas here since it is here what is that, there will be manometric fluid here at a certain height of this 0.1 meter. So, you can calculate what should be the pressure there. So, it will be coming as P gas plus here 0.0194 atmosphere. So, finally, at the equilibrium condition, you can say that Px will be is equal to Px dash. So, if you substitute that Px and Px dash here, we can say that P gas minus P atmosphere, that will be coming as 0.0038 atmosphere. So, finally, this will be regarded as gas pressure. If you subtract that atmosphere pressure from its absolute pressure, then you can calculate what should be that gas pressure, it will be P gas minus P atmosphere. So, it will be 0.0038 atmosphere. Now, the contribution to the hydrostatic head from the gas bubble can be ignored, since gas densities can be neglected here relative to the liquid densities. So, that you have to remember. Another example is given here, air is flowing in a circular pipe during its supply to a fluidized bed reactor connected with a closed end manometer to measure its pressure. The manometer fluid density is given to you. An air bubble was seen trapped in the left leg of the manometer during the process. The closed end of the manometer is in a vacuum. So, what should be the pressure of the air flow in the pipe? Similarly, you have to calculate the pressure at its x point and also pressure at its x dashed point here. So, similarly you can get that Px as 1.77 centimeter mercury, whereas Px dash you can get that here 0.3 centimeter mercury. So, after balancing these you can easily calculate what should be the that gas pressure inside the pipe. Another example where you will see that to measure the pressure drop, if you are using multiple of fluid as well as that you are using that manometer in different way. If you design the manometer in different way, how to calculate that pressure drop measurement. Now, as shown in here in the figure, you will see that you have to measure the pressure between 2 points of pipe A and B, and the manometer like this designed here as shown in figure is connected to this process unit at point A and B, and you have to calculate what is the pressure difference between A and B. Now, in this case the manometer is filled with that some portion is water, some portion is with mercury, some portion will be filled with oil, and again some portion will be as mercury and water like this. So, here three different fluids are there inside the manometer. So, you have to calculate that pressure between A and B. Now, you have to use that general equation of that hydrostatic pressure, that we know that P 1 minus P2, that will be equal to minus rho G into Z1 minus Z2. So, this is your general equation. If you apply this general equation, you can easily calculate what should be the pressure difference between A and B. Now, how to apply? Before going to apply these things, you have to mark it out at different interfaces of the fluids inside the manometer. Here like this, here this is one that interface, this is regarded as 1, this is another interface that is regarded as 2, and another interface 3, and like this another interface 4. So, after giving this marking of 1, 2, 3, 4, we have to calculate the pressure between these points. Like here, if we consider first the point A and 1. So, what should be the pressure between these 2 points A and 1? That means, here according to this hydrostatic equation, it will be Pa minus P1. So, for that minus rho into Z into Z1 minus Z2. What should be that? Here rho, here in this case rho will be of water, because this portion is filled with water. So, that is why minus rho W into Z into ZA minus Z1. What is the ZA? Here we are taking the reference line or datum line from this bottom of this manometer, and the Z direction is upward direction. Here this is positive Z direction. So, if we consider that ZA minus Z1, it is simply what is that positive value. So, what is the length of that? It is given here 10 I think centimeter. So, what will be the meter? 0.10. So, finally, after substitution of that, water density and the gravitational acceleration, and then finally you are getting this equation. Similarly, if we consider this point 1 and 2, then you will see that here density of the fluid will be mercury density like this here rho m, whereas the distance between these 2 points here Z1 and Z2, in this case here see Z1 is lower point, whereas Z2 is higher point in the positive Z direction. So, here the difference will be negative. So, that is why it is coming as here in this case after substitution of density of mercury, gravitational acceleration, and difference of Z1 minus Z2, it will be minus 0.03. Similarly, between 2 and 3, here again P2 minus P3, it will be like this, density will be of fluid oil. So, in that case, here again after substitution, here in this case Z2 minus Z3, it will be positive. So, it will be plus 0.04. Similarly, for others P3 minus P4, it will be between 3 point and 4 point. So, here it will be is equal to, again here density of the fluid will be of density of mercury. So, here after substitution of that, and what will be the distance between that, it is given, it will be 0.05, but it will be negative because here 4 point is higher than the 0.3 in the positive z direction. Similarly, here P4 minus Pb, between this 0.4 and B, it will be coming there. Here again this fluid element will be only water. So, because of that you have to consider the density of water there. So, finally, if you sum it up all those pressure differences at different points, you will see that after summing up, here you will see cancelling of this P1 P2 here and P2 P2 here, P3 P3, P4 P4, finally you are getting that PA minus PB, that will be exactly after that calculating from this right hand side of this equation and summing up, you will get this 10131.768 Newton per meter square. See how simple this calculation of the pressure drop from its that system by using different design of that manometer, by using multi fluid inside the manometer, just by using simple hydrostatic equation of P1 minus P2 will be equal to minus of rho into Z1 minus Z2, this equation. And another example here given, if it is suppose inclined tube, also you can calculate. Please go through these slides here also. In the same way we have calculated that here what will be the pressure difference between A and B if the fluid is flowing through that inclined pipe of 30° angle there, and the length between these 2 points is given as L, and at different interfaces of the fluid whatever it is being given, the length is given there. So, finally, at the same principle you can use this problem to calculate that pressure differences as Pa minus Pb, and you can get this equation, and finally you can get this pressure difference here. Similarly, another like LPG is kept intact in a tank as shown in figure here. So, what should be the pressure exerted if you are using that that inclined manometer? Here also same way you have to calculate, but only thing is that height will be considered as what is that height here from the inclined length that you have to calculate. So, accordingly you can get the pressure difference. Now, temperature, that for the process analysis, temperature is one of the important variables, because this temperature of course will that influences that reaction, even other processes, even physical separation process, reactive separation process, even many chemical engineering operations, those are actually depending on the temperature. So, that you have to know that temperature, how that temperature will be distributed, even how the temperature will be measured, and also what are the different units are considered to calculate that temperature in a particular system. Similarly, the same way different systems you can get as pressure also, temperature you can measure by different unit, even some sophisticated instruments like thermocouple you can use, even the thermometer you can use, even other different types of that sophisticated instrument of measuring this pressure temperature are available, and devices are available to measure this temperature. There are different systems like Fahrenheit, Celsius, Kelvin, even Rankine. These are the different units are generally being used to express that temperature like this, and there is a certain conversion factor to convert one system to another system for this temperature. So, please remember this conversion equation of this temperature from degree Fahrenheit, from this centigrade Celsius, even temperature in Kelvin from Celsius, even temperature from Fahrenheit to Rankine, even temperature from Kelvin to Rankine, like this. So, these equations will give you that how to convert this temperature unit from one system to another system. Basically, in SI system always you have to use that Kelvin unit, and if any problem is given in terms of Celsius, then you have to convert it to Kelvin just by adding 273.15 there. So, we have discussed these process variables of pressure and temperature in this lecture, and how to estimate that pressure or calculate that pressure from the basic fluid static equation, and how to derive it we have discussed. I think it will be helpful for your further understanding of the calculation of the process, and you have to remember certain things of that hydrostatic equation, and also how to use that hydrostatic equation to calculate the pressure by the manometer. So, next lecture we will discuss the other things of that basic calculations of this chemical engineering, like what are the rate of different process, how to calculate that rate of different processes which are involved in chemical engineering system. Thank you.